Hi. So we'll continue to see some applications of open mapping theorem, closed graph theorem, and uniform Bourdieu's principle. So let me recall the open mapping theorem. Okay, so Nirupama proved the following. So if you have Banach spaces, XY or Banach spaces, and T is a bounded linear map. It's a bounded linear map. And it's on to T. And then T is a open map. Is an open map. That is, it takes open sets to open sets. Okay, so we don't actually need it to be onto. The Banach space requirement is important. So we can equivalently say that if T xy is Banach, again we should have xy to be Banach spaces, xy Banach spaces. And this is an equivalent form. The same thing. So if T is a map from x to y, bounded linear, then T is open if and only if T of x is closed. It's an if and only if. So one condition is clear. You can replace y by T of x, I mean the range of x, and then use the open mapping theorem, and that will prove that if T of x is closed, then T is open. So if it is open, then it is also T of x is closed. I think that's also, I think she proved. I'm not sure, but it will follow from this. So one way is clear. One way is you can just take the range to be T of x. So if it is closed, it's a Banach space. It's a subspace of closed subspace of Banach space. So it's a Banach space. So using open mapping theorem, you can conclude that. So the other way, if T is open, then that implies T is bounded below. So I think she proved it. Otherwise, also it's not difficult. You prove that T is continuous if it is bounded. No, the same thing will imply that continuous means the inverse image of open set is open. That will imply that that is equivalent to saying T is bounded above. So similar thing will work here, bounded below. So it will. You can imitate that proof. I think that's what she did, and she proved it. Okay. So this is equivalent to saying there exists a k greater than zeros. K greater than 0 such that Tx is greater than or equal to k times x for all x and x. Okay. So now this implies that the range is closed. Suppose you want to prove range is closed. So suppose, I am assuming T is open. I want to prove that the range of T is closed. So suppose there exists a T of xn containing in y. T of xn converges to y, then I have to prove that y is also in the range. So because of this, T of xn minus xn is greater than or equal to k times norm of xn minus xn. To have this, okay, because it's bounded below. So since this goes to 0, this is a Cauchy sequence. This implies that xn is a Cauchy sequence. Cauchy. So since it is complete, xn converges to x. Okay. Now txn converges to tx, and which should be equal to y because the limit is unique. So this implies the range T is closed. Okay. So we can restate the open mapping theorem as if you have x and y are Banach spaces and T is a bounded linear map, then T is open if and only if T of x is closed. T is open if and only if T of x is closed. So using this, you can, I think that also she concluded. I am just recalling to get a feeling. I'm just recalling all these things. So we have the following corollary. If T is a map X to Y is a bounded, linear, and bijective, okay, then T's inverse is also bounded, which is of course linear, is bounded. So T is an open map. It takes open sets to open sets. That inverse T inverse brings open maps. I mean, the inverse image of T inverse, which is T of U, is open. So which is for continuity, which ensures the continuity of T inverse. Okay. So in this theorem, the Banach space assumption is important. I think she gave an example, but if I remember, her example was to do with some sequence. So you can take this example. This is also so example, and this is counter example. Counter example. So if xy is not, if y has to be, the y has to be a closed subspace. That is important. So consider the integral operator t from t from C01. I mean, mostly this will be our counter example for all these theorems. C101. Okay. So where t of any f at x equal to integral 0 to x f of x dx. Okay. T is linear clearly, and t is bounded. You can clearly see that t is bounded. Is bounded. I mean, you just say take the supremum now of f of x, that will be smaller than 1, right? Yeah, 0 to 1. So the norm of t will be smaller than 1. Okay, it's a contraction. So but t is not 1 1. So you can take you take x to be C01 quotiented with this equivalence relation. That is, f is equivalent to g if f minus g is a constant. Is constant. It's a constant function. I mean, is that right? Yeah. So then this is 1 1. Right? I mean, the inverse then t define t. I still define okay t tilde from x to C01. Okay. And that will be up to a constant, no? Is it well defined? No, that's okay. It is from 0 to x. I mean, I think it's okay. So yeah, but you can take some two functions and that will differ by a constant. So it's not well defined. Well, I want to show that this maybe this is not needed. I just basically want to show that t is not bounded below. So we have, see, this function is not 1 1, but if you up to constant, the inverse image, the inverse of this map t is the differentiation, right? And that is not bounded. So t is not bounded below. That's what I want to say. See the thing is, let's see if tf norm of tf. Okay, I want to say that so let's take this. Let's take this exponent.
Sir,
yeah.
After bounded, what is written in the bracket?
Where? What?
T is last line. T is linear. T is.
Where in the top?
No, last line.
T is linear.
Yeah,
T is
T is
bounded. It's
as
clearly bounded. Yeah, exercise.
oh, okay.
I have said it's exercise. Okay, I orally said it, so you can exercise. You verify it. Okay, verify. I mean, I have already given an example. I mean, I have already given an exercise. I don't know whether it was an assignment. The integral operator here. I mean, you can multiply by a function of two variable k, x, y, and you get an operator. Okay, so here that map is just identity. Okay, so I want to prove that. So this okay, let me take an xn. We take xn or xn, txn. Then so should I take n times xn minus? Let me see. So no, suppose I want to prove that. I mean, if t, I want to prove that t is not bounded below. So, but t is linear, t is bounded, and t of I mean, but t is not bounded below, right? I mean, if I mean this is just a counter example. I want to say that if that range is not closed, then it will not be an open map. If it is an open map, then the range is, I mean, the range. If it is, I mean, if it is not an open map, the t is not, I mean, t is not bounded below, which is equivalent to saying t is not bounded below. I am saying t is not bounded below. T is not bounded below. Bounded below means that is that does not exist a constant k such that t of x is greater than or equal to k times norm. I mean, t of f is greater than or equal to kf. So if this exists, I mean, this will just mean that if tfn converges to 0, then fn should converges to 0. So xn by n should converges to 0. Okay, this function converges to 0. But if I integrate, that will not work, right? So no, it's the other way, right? It's the other way. Txn converges to 0, then that does not mean so. If you take fn equal to xn, x power n. This is, I mean, t power n or x power n. Then tfn can converge to 0. Tfn equal to, what is tfn? Which is just integral 0 to 1 xn dx. Okay, which is just xn plus 1 by n. Xn plus 1 by n plus 1. Okay, so which will go to 0, right? As n goes to infinity. Okay, but norm xn, I mean, this is the function. This is a function which will go to 0. I mean, the norm of this. Norm of tfn goes to 0. But norm of fn equal to 1. Okay, the infinity norm equal to 1. So fn does not go to 0. Okay. So t is not bounded below. So t is not an open map. Okay. So this is a counter example to say that the range is closed is strictly needed. Okay, otherwise this is not true. Anyway, is it clear? So all I'm saying is, if you take the integral operator, the inverse, it's not, I mean, it's not inverse actually, because it's not 1, 1. So up to a constant, that is the inverse. So the inverse is the derivative, the differential operator, and the differential operator is not bounded. So instead, I have proved that it's not bounded below. Okay. So we will say, I mean, we'll come to this again. They talk about this differential operator again. So we will see some corollary of the open mapping theorem. The first one is, see, I hope you know this. So if you have in a finite dimension, it's not working. So in finite dimension, any two finite dimension, any two norms are equivalent. Any two norms are equivalent, right? I hope you know that. Do you know this? I mean, it was. I hope it was done in the last semester. Everyone knows this.
Yes.
Yes. Okay. Good. So that is, there exists constant. There exists k greater than 0, such that norm x1 is k times this is less than or equal to norm x2 less than or equal to k times norm x1 for any two norm 1, norm 2. Okay, on finite dimensional space. But infinite dimensional, this need not be true. Two norms need not be equal. But then using open mapping theorem, we can prove that if you have two norms on a Banach space, both forms a Banach space. See, infinite dimension things can be complicated. You may have two norms, and if you, I mean, with respect to one norm, it may be a Banach space, and with respect to the other norm, it may not be a Banach space. Suppose you have two norms with respect to which it's the Banach space. Okay, I mean some vector space is a Banach space with respect to two different norms. Then they are either equivalent or they are both inequivalent, in the sense that one, I mean, there will be a topology, then the topology given by both the norms are same, or it's not the case. I mean, they have nothing to do with that. I mean, it's not that one is a course of topology or one topology is contained in that. It cannot happen like that. Okay, that's what this is. So if X is a non-linear, so X is just a vector space, X is just a linear space, and X is a Banach space, with respect to norm 1 and norm 2. Okay, with respect to both the norms, it's complete. Okay, and suppose, I mean, only the statement is the proof is just immediate. Suppose there exists a k greater than 0 such that norm x1 is less than or equal to k times norm x2. Okay, that is this. This means that the norm. I mean, this means that if the two norm is stronger than the one norm, that is the topology given by this one norm is contained in the topology given by the bigger another norm. Okay, but then they are actually equivalent. Then there exists a k greater than 0 such that norm x2 norm x2 is less than or equal to k times norm x1. Okay? So they are equivalent. It's not the case that one topology will be coarser than the other topology. It will be the case that both the topology is same. The topology, I mean, the norm may be different, but then the topology given by both, I mean, norm, see, the norm determines the geometry of the Banach space. Okay, but then the topology, I mean, see, we have, for example, in the finite dimensional, we have L1 norm, we can have L1 norm, L infinity norm, L2 norm, LP norm, anything. But then the topology given by all the norms are same. The convergence will be same. Topology means either open sets is same as closed sets are same. That means the convergence is same. But then the geometry may not be same. For example, if you take the unit ball or something, it may be different for each norm. So here the norms may be different. The geometry may be different. Geometry of the Banach space may be different. But the topologies will be either same or it has nothing to do with each other. I mean, one may not be contained in the other. Okay, so that's what will happen, provided both forms a Banach space. Both norms, I mean, this vector space is a Banach space with respect to both the norms. The proof is immediate. You just take T from X to X, identity map, Tx equal to X. Okay. Then if you consider, maybe I will write it with a norm. So what I have written, the first thing is T of, so we have that norm of suppose there exists a k such that norm x1 is less than or equal to k times norm x2. Okay, then this map, then T from X with norm 1 norm 2, sorry, x with norm 2. So this is tx. So norm 2 to x with norm x with norm 2. No, so this is norm 1, sorry. Norm 1. So this is continuous. So I mean the tx is, this is tx with respect to norm 1. So this is continuous. Okay. But this is a bijection. So by open mapping theorem, when they both of them form Banach space by open mapping theorem, T inverse is continuous. So this implies there exists a K such that norm x2 is smaller than K times norm x1. Okay, so both the norms are equivalent, or otherwise they have nothing to do with that. Okay. So if one norm dominates the other, this norm also dominates the other one. Okay, so the topology is same. Okay. So we have another corollary. You can have the direct sum norm, for example. So if x equal to x1 direct sum x2, this is just algebraic direction. Okay, algebraic direction. That is, for all x in x, there exists x1 in x1 and x2 in x2. It will be unique such that x equal to x1 plus x2, and x1 intersection x2 is empty. Sorry, trivial. So that's what it means by direct sum. It's algebraic direct sum. Then we can there exists a C, there exists a K greater than 0 such that norm x is greater than C times the K, mean I have written K, sorry. K times norm x is greater than norm x1 plus norm x2. If x equal to x1 plus x2, x1 is in x1, x2 is in x2. Okay. I mean, this proof is immediate. So define norm 2, norm x2 by norm x2 equal to norm x1 plus norm x2. Said norm norm x1 1. Oh, there is only one norm, sorry. By norm x2. Okay. Then by triangle inequality, we have norm x1 plus x2, norm x equal less than or equal to norm x1 plus norm x2, so which is equal to norm x1, right? So this implies, by the earlier theorem, this implies there exists a K such that K greater than 0, such that norm K times norm x is greater than or equal to norm x1 plus norm x2. So this is just an application of the open mapping theorem. And so, I mean, the basic, usually the application is, if you have a bijection, then the inverse is automatically continuous. So that's the most important thing. So now we will see some application of closed graph theorem. I don't know, I don't remember any other application of any immediate application of open mapping theorem. You'll see, of course, closed graph theorem itself is an application of open mapping theorem. We use for open mapping theorem to prove closed graph theorem. So let's see some closed graph theorem. Application of closed graph theorem. So the closed graph theorem says the following: X is a Banach space. It's important that X is a Banach space. Okay. And Tx from Y is bounded linear. Sorry, it's not bounded linear. T is linear. in here. Then T is bounded is equivalent to saying G of T, graph of T is closed. Graph of T, as you know, is just XTX. X in X is contained in X cross Y. Okay. So X cross Y as a product, it's a product space. And you can define a norm by taking some of the norms. Okay. So there the graph is closed. But then you don't have to, this is just equivalent to saying, so equivalently. So if you want to prove, one way will be clear. T is continuous, the graph has to be closed. Okay, T is continuous. That means Xn converges to X, T of Xn will converges to T of X. Okay, so you can see the graph is closed. So the other way is the useful thing. So how do we check graph is closed? See, the nice thing is, if you want to prove that something is continuous, then you have to prove that if Xn converges to X, T of Xn converges to T of X. But then you don't need that much. Using the closed graph theorem says the following. So if T is a map from X to Y, X is Banach space, is linear. Okay. So if you have a sequence, if any sequence for all Xn contained in X, okay, such that Xn converges to X and Txn converges to some Y, you can assume this convergence. T of Xn converges to some Y. Okay, this is what it means by the graph is closed. Graph is closed means Xn converges. So you have this Xn graph is closed. Some limit in the graph means X Txn converges to some Xy, right? That's what it means. It is closed means this Y has to be equal to the Tx. That's what it means, right? So then T of X equal to Y. Okay. So usually if you want to prove something is continuous, then you have to prove that Xn converges to X implies Txn converges to Tx. Okay, that will be more difficult. Here you can assume the convergence of Txn, X. So you can Xn converges to X, Txn converges to Y, then Tx equal to Y. So this is what you need to verify for the graph to be closed. So to apply this closed graph theorem, it's important that X is a Banach space. Okay. Okay. So this is closed graph theorem. So again, closed graph theorem will not work if this is counter example. Will not work if X is not a Banach space. So for example, define T from C1, 0, 1, which I have already defined. This is equal to all those f in continuous functions in 0, 1, such that f prime exists, and f prime is in C0. F prime is also continuous. Okay. This is just the inverse of the integral operator we defined. So Tf equal to f prime. This is the differential operator. Then you can see that the graph is closed. Then graph of T is closed. The C1 Z01, which is contained in C01, this is not a Banach space. This one differentiable function is not a Banach space with respect to the uniform norm. It is Banach space with respect to some other norm. Okay, you can define a different norm and it will be a Banach space. Okay? So this itself shows that, see, the C1 01, you can define a norm like this: f infinity plus f prime infinity. Okay, it will be a Banach space with respect to this norm, and that is contained in the proof that G of T is closed anyway. So, but it is not closed with respect to only f infinity. Okay, it's not complete with respect to that. It's not closed inside C01, which is equivalent to its complete. Okay. So G of T is closed. So I have to prove that G of T is closed. The graph is closed. Why the graph is closed? So if Fn converges to F and Tfn converges to some G, that is Fn prime converges to, Fn prime converges to some G. Okay, that is. Okay, then F equal to G, F prime equal to G. This is clear. This follows from, this is an exercise. is exercise in basic analysis. If a function, sequence of function converges to some function, some f, and its function converges to f uniformly, okay, then the limit is continuous. Then f1 prime converges to some g uniformly, then the derivative, then the derivative of f is g. This will, you have to use mean value theorem to prove this. Okay. So you can check that. This is a basic theorem. Okay. So I talked about it in the some second class or first class or second class. I don't remember something about. I think I defined the other norm. Some time back I defined a different norm on C1 with respect to which it is Banach space. So there also this is used. Okay. So because of this, the graph T is closed. So is it clear? The graph T is closed. Okay. But we know that T is not continuous. But T is not continuous. It's not bounded continuous. It's same thing. Again, the same example. Xn. Xn. So this map. Take Fn equal to Fnx equal to x power n. Okay. Then Fn convert, then x power n by n maybe. Okay. Then Fn converges to 0. Okay, but Fn prime equal to Fn n into x, so x power n minus 1. So this has norm 1. It does not converge. So if norm and everything, everyone has norm 1, so it does not converge to 0. Fn prime does not converge to 0. Okay. So it's not continuous. So the assumption that the X is a Banach space is important for closed graph theorem. Okay, so now we use the closed graph theorem to prove application of closed graph theorem. So to prove that, I need to say the following. P is a map from X to X. Okay. I want to talk about the projection map. So suppose, and it satisfies the following: P of x, P of x equal to, P square equal to P. That's what I want to say. I can say something else. Okay, P square equal to P. Okay. So there is no star structure. This is just a Banach space. X is a Banach space. Okay. And we have P square equal to P. If we have any vector space, if we have a linear map, which is a linear map satisfying P square equal to P, then X looks like this. X is a direct sum. This is algebraic direct sum. Range of P, direct sum, kernel of P. Okay. This is just clear. If we have X in X, then X equal to Px plus identity 1 minus, this is identity minus Px, right? Now Px is in range of P, and P of I minus Px equal to Px minus P square x equals 0. So I minus Px is in kernel of P. Okay, so, and we know that kernel of P intersection range of P. You can see that if X is in, you can see that the kernel range intersection is also 0. So because of this, if you have any idempotent P square, that is P square equal to P, then X looks like, X is a direct sum of range P and kernel P. It's an algebraic direction. But in Banach space theory, when we say direct sum, we would like the subspace to be closed also. So that is this proposition.
So what is this I represent?
I is identity.
Identity map.
Yeah, identity map. Either I use 1 or I, okay, whenever. So X is a Banach space. P is a map from x to x, P square equal to P, a linear map, P square equal to P. Okay. Then P is continuous if and only if both range of P and kernel of P are closed. Okay. Okay. Proof, we want to use closed graph theorem. So first, if P is continuous, we don't need closed graph theorem for that. P is continuous, then the range of P is closed. That is clear, no? So P is continuous. So we want to prove that range of P is closed. So that is if we have a yn contained in range of P, that is yn equal to Pxn for some xn, okay, and yn converges to some y, okay, then we have to show that that is also in the range. But I mean, y will itself will be, I mean, it satisfies P of yn equal to yn, so it will satisfy. So then P of yn equal to P square xn equal to P of xn, which is equal to yn. Okay, so this implies P of yn. So this implies P of yn converges to P of y. So this implies P of y is also y, right? P of yn converges to y. This implies P of yn. So if we assume continuous, P of y converges to P of y, and these are all equal to yn, and this is equal to. So this, I mean, this also converges. This is equal to yn, and yn converges to y. So these two things should be equal, right? Maybe I can do this. This implies this implies P of y equal to y. Okay, so that implies y is in the range of P. Okay, I mean, if you take some yn in the range of P, then yn will look like P of x. I mean, then P of yn will look like P of xn. Because of that, P square xn equal to P of xn, which is equal to yn itself. So P of yn is yn. So P of y is also y. That implies y is in the range. Okay. Similarly, you can apply I minus P and prove. I mean, so yeah, if something is continuous, then the kernel for any linear map, if it is continuous, then the kernel is closed. So that is true for any linear map. Also, kernel of P is closed. For any linear map, this is true. I mean, if some linear map is continuous, then the kernel of P is closed. I mean, for any continuous map, that is true. If xn, I mean, P of xn equal to 0, then P of xn converges to something, then that will also be the limit also converges to 0. Okay, so kernel of P is closed. So we need to prove the other way. So suppose range of P and kernel of P are closed. Then we want to say P is continuous. Then we want to say P is continuous. To prove P is continuous, so that is the statement in the proposition. P is continuous if and only if range of P and kernel of P is closed. So suppose range of P and kernel of P are closed, then we need to verify the statement in the closed graph theorem. So suppose there exists suppose we have xn contained in x, and xn converges to x, and pxn converges to y. Then we have to prove that but then pxn converges to y. Then we have to prove that y equal to px, right? So range of P is closed. So there exists since range of P P is closed, y should look like y equal to some P. I mean, y looks like some px, so that will imply by the earlier what we have noticed, since range of t is closed, p of y equal to p of y equal to y. P of y equal to y. So this implies p of y equal to. So what do you have to prove? We have to prove that px equal to this. So pxn converges to px, right? Px. So this is so, and we know that pxn converges to y also. Pxn converges to y, which is equal to py, which is equal to we have to, what do we have? We have to prove that y equal to px, right? So pxn converges to y. It's just clear. I mean, but since range of p is closed, y is also in range of p. So p of y equal to y. That is right. Now we have to prove that pxn converges to y. So which is equal to py, right? Which is equal to py, and what is the? Oh, I have to use the I minus p. The kernel of p is closed. That's also I have to use. So I have to use both of them. So I have used that y is in the range. On the other hand, I minus p. I minus p. So I minus p of xn. I minus p of xn equal to no, I minus p of xn. Right. Equal to 0 is in kernel of t, right? Now p of xn. Now p of so what is it I have to prove? Xn minus pxn, right? Xn minus pxn is in kernel of p, right? Right. So xn minus pxn converges to x minus pxn converges to y, x minus y. Xn minus x minus y. Okay. Now these are all in the kernel of y. So x minus y is in kernel of p. That is I minus p of x minus y equals. So p of x minus y is 0. This implies px equal to py equal to y. Shoot. So the graph is closed. P of x equal to, so graph necessarily got confused.
So,
Is there a problem?
so how py equal to y came? Py equal to y.
Yeah. Y is py equal to y. Because that is in the range. Y is in the range of that. So let me go through the whole thing. So I am using I'm using the assumption that I want to prove that the graph of P is closed. I'm assuming that range of P is closed and kernel of P is closed. Okay, the range of P closed implies that Pxn converges, we have Pxn converges to Y, then Y should be in the range. Okay, because range of P is closed, so Y should look like Py equal to Y. I mean, range of P, something is in the range of V means we have noticed here. If you, I mean, because P is an idempotent, if you assume, I mean, if you apply P again, P of Y equal to Y. On the other hand, the kernel of P is closed. So xn minus Pxn is in the kernel of P. Okay. So that which converges to x minus y, and x minus y is also in the kernel of P because we have assumed kernel of P is also closed. So P of x minus y equal to 0, which implies P of x equal to P of y and P of y equal to y. So this implies Px equal to y. This is what it means by graph of P is closed. So P is bounded. Okay. Any doubt? Anyway, I think only by writing it you will get convinced. Okay. I hope it's fine. Okay. So this is an application of closed graph theorem. So what else? Okay, Ayan, this is my favorite application of closed graph theorem. So, okay, so if we have a map, suppose, so XY are Banach spaces, assume XY are Banach spaces. Okay. T is a map from X to Y. Okay. Then define T star, a map from Y star, dual of Y to the dual of X by. So we want to define a map from Y star to X star. So if we have a linear functional in Y star, okay, if you take a phi in Y star, we have to get a linear functional on X. So that is T star of phi. We have a map from X to Y. X and Y are Banach spaces. Then we want to define a map from Y star to X star, the dual of Y to dual of X. So we take a linear functional on Y, which is phi in Y star. Okay, then T star phi acting on X. We have to get a functional on X, which is equal to phi of Tx. Okay. X in X. So this map is well defined, clearly defined. The definition is not a problem. Okay. Then we want to, so if T is bounded, then we want to prove that T star is also bounded. So why is T star bounded? That is T star of phi at X, okay, is less than or equal to, this is which is equal to phi of Tx, which is less than or equal to norm phi times norm Tx, which is less than or equal to norm phi times norm T times norm X. Okay. So these things implies first, also sorry, this is where I am sorry, I am verifying that it is actually well defined. Sorry. So this implies T star phi is less than or equal to norm phi times norm T. So this implies T star phi is indeed an X star. Okay, so this implies T star phi is well defined. So this is where it is well defined. T star phi is well defined. Okay, so if you just notice, I have a map from X to Y. Then I define a map T star from Y star to X star by this prescription. Then I have just written down the definition of boundedness. Then I verified that T star phi is indeed, T star phi is a bounded linear functional. So T star, I mean, as a linear functional, it is defined, but it should land up in X star. So that is what I have verified. So it's a T star phi is a linear function. It's a bounded linear function. So T star phi is well defined. It's a bounded linear functional. Further, we have T star phi is less than or equal to this, which implies norm of T star is less than or equal to norm of T. Okay. So T star is bounded. Further, we can actually prove that T star T is equal to T because by the same prescription, there exists a T star is bounded. So there is a T star star from X star star to Y star star. Okay. With, you have already verified. I mean, when you can go from T to T star, then you can go from T star to T star star. And the T star star satisfies this, equal to norm, is less than or equal to norm T star. But this T star star, you can restrict it on the X hat. on x hat equal to t of x. You can verify that. That is t star star acting on x hat. X hat, you know, x hat of any phi equal to phi of x. Okay, if I mean this we have defined when we discuss reflexivity and other thing. Let me recall that. Where x hat is an element of x double star, which is defined by x hat. X double star means it is defined. It's a linear functional on x star. X double x hat acting on phi is phi of x. Okay, for x in x. This is for all phi in x star. Okay, and we have seen that this is a bounded map. It has the same norm of x. Okay, so now we have this. We want to verify this. Okay? This verification. T double star of x hat. Okay, acting on phi. By definition, this is equal to phi of t star of x hat acting on phi, which is phi acting on, so that will not work. No? T star is a map from T x hat acting on, I mean the phi is that way, sorry. This phi is T x hat acting on some, maybe I should use chi, where chi is in y star star, okay, which is equal to chi acting on, here I should get the T star of x hat, right? And T star of x hat, that's right.
Won't it be x hat of?
Say it again.
Won't it be x hat of t star of phi or?
X hat, sorry, the x hat. No, I'm verifying this thing. T star of x hat equal to tx, right? I mean t. Sorry, this has to be a hat. Sorry, yeah, you are right. Is this what you are saying? Is this what you are saying? Is that what your question is?
Okay, now it's okay. Yes.
Yeah, this is what I'm saying. So T star star of x hat acting on some chi. Chi is something in x. I mean, sorry, chi is in y star, right? T star star of x hat. T star star is a map from x double star to y double star. So T star star of x hat should be acting on something in y. Chi is in y star, right? Right. So yeah, chi acting on. So this is just x hat of, sorry, x hat of chi acting on T star of, not chi, x hat acting on T star of chi, sorry. Now it looks okay. So that is equal to x hat. So that by definition, x hat of T star of chi, and we have just written it here, which is T star of chi is just chi of chi acting on.
T star chi means chi of T star.
Chi of T star of chi, which is what chi of T star, which is just chi of no, there is no T star, no? So there is no T star. Wait.
The second line x hat of chi of T star.
What is it?
Uh,
No, there is
x
no
hat
T star.
of
There is no T star. Wait. I'm getting confused. Wait. I didn't sleep properly. What is the definition here? T star of chi at x is phi of that tx, right? So this is just chi of T star of V at this equal to, yeah, we have T, so we have a T, we get a T star, and from that we got T star star. So we have it, we have started with a T, right? Right. So this is equal to chi acting on chi of x hat of T star. This is equal to, I was right, x hat of T star of chi, okay, which is equal to chi of, yeah, x hat of T, which is equal to, I mean, by definition, this is just T star of R. So this is just by definition, which is just T star of chi acting at x, right? That is by definition chi of Tx. Good. Which is equal to, now it's correct, which is equal to Tx hat acting on chi. Okay. So this implies T double star of x hat is nothing but Tx hat. Okay. So as it is, this T, this means T double star coincides with T on the, I mean, coincides with T on the subspace. I mean, X embeds, see, the point is this X embeds in X double star as a subspace. Okay. And T coincides on this X. Okay. T, I mean, T star coincides with T on X. Okay, T star star is defined on X star star, and it coincides with T on X. So this implies norm of T star star is greater than or equal to norm of T. Okay, so that's what we have already, this is true, and we have already seen that norm of T star star is less than or equal to norm of T star, less than or equal to norm of T. Okay, so now we have proved that that is less than or equal to this. This implies norm of T. I just want to prove this. Norm of T is equal to norm of T star. I mean, it is to prove this, I went through all these things. Let me tell you the philosophy again. Okay. If we have two Banach spaces X and Y, if we have two Banach spaces X and Y, and we have a linear map T from X to Y, which is bounded, then we can define an adjoint map T star from Y star to X star by this prescription. Okay, which by this prescription. T star phi at x equal to phi of tx. Okay. Then this T star is a bounded map, and by considering the, then it is also true that norm of T star is less than or equal to norm T, that I have verified here. But since norm of T star star is less than or equal to norm T star, then I verified that norm T stars, the T stars are restrict to T on the subspace. I mean, where X sits in as a subspace in X double star. Because of that, all these norms coincide. Okay, that's what I have proved. Anyway, we don't need all these things for this closed graph theorem. For the closed graph theorem, this is the proposition I want to prove. This is just the other way to this. I mean, what this says, what we have seen is, if we have a bounded linear map T from X to Y, then we have an adjoint map from Y star to X star. If T is bounded, we have used the fact that T is bounded. Closed graph theorem provides with something else. So suppose X, Y are Banach spaces. They have time. I will take some. Since I came 10 minutes late, I will take 5 minutes more. So X, Y are Banach spaces, and T from X to Y is a linear map. Is linear. Okay, and there exists S from Y star to X star, which is like this T star, such that S of phi at X equal to phi of Tx. Okay. I mean, this is like the star map only. You can, if you want, you call it T star, whatever. I'm not assuming any of these things bounded. T is need not be bounded, X is not bounded. Suppose if it exists, okay, then T is bounded and S is also bounded. Hence S is also bounded. And we have already verified norm T equal to norm S. Okay. I have to verify that T is bounded. So this is the statement. I mean, this says that if you have a linear map for which the adjoint exists in this sense, okay, in this sense, then it is bounded. That's what this says. So the proof is direct. Maybe I should leave it as an assignment. Okay, I will do it. So you have to verify that. What do you have to verify? You have to use the closed graph theorem. You want to prove T is bounded. So suppose Xn converges to X. Okay, Xn contained in X, and Xn converges to X, and Txn converges to Y. You have to prove that. Tx equal to Y. Okay, but then Xn converges to X. Okay, then phi for all phi in X star, phi of Xn will converges to phi of X, right? Okay, that's right. And phi of Txn will converges to phi of Y, right? So S of phi dx, S of phi x, you can if I write it in this way, it will be clear. We have Xn. We have to, what do we have to prove? We have to prove that Tx equal to Y. Want to prove Tx equal to Y. Okay, by Hahn-Banach theorem, it is enough to prove phi of Tx equal to phi of Y for all Y. Phi of Tx and converges to phi of Tx. This is equal to S of what is it? S of Vx. S of phi at Xn. Okay, S of phi Xn converges to phi of Y. But then S of phi is a linear function. Okay, so this should converge to S of phi at X. S of phi at X. But then that is equal to phi of Tx. Okay, so this implies phi of Tx equal to phi of Y for all phi in Y star. This implies Tx equal to. So by closed graph theorem, closed graph theorem T is. Yeah, the full screen is not there. I mean, I have proved that the graph of T is closed. If Xn converges to X, Txn converges to Y. I have used the fact that S is just a linear map, but then S of phi is also continuous linear functional. S takes Y star to X star. That's what I have used. Okay. S of phi of Xn converges to S of phi. So S of phi of X equal to this. Sorry, if you have a doubt, you ask me. I couldn't write the whole thing in one page. Sorry. Is this okay? If you look at it, it will be okay. If it's not okay, you ask me in the next class. Okay. And Wednesday, we are not having class. Anyway, I will stop recording and then we'll